Okay, good afternoon, ladies and gentlemen. This is Professor David J. De Los Reyes. For this afternoon, I will be having a long video format topic, and this is a continuation of my direct current circuit. This is a long video format, so we are discussing concepts and example problems over here. It's not just only problem solving. We are discussing the concept of every topic. Okay, let's proceed. The subject matter for this afternoon will be a continuation of a direct current circuit, and this will now be lesson number 3. Okay, so for those of you who are planning to take up electrical engineering, this is for you guys. The title of the topic will be series connection problem, or this will now be a problem solving on the topic series connection. For us not to be bored, I will be giving an actual problem here. So they could not say that we are bogus, you know. We are solving a real problem here. Okay, let's proceed. To illustrate a series connection problem, this will be the figure. Okay, I'll give you the figure. The voltage source is a battery. It could be a battery or maybe a direct current generator. Okay. The first load is a lighting loads. The total wattage of the lighting loads is 600 watts, meaning it could be 6 light bulbs maybe, in which, okay, the rating is 60 watts, so the total wattage is 600 watts. Okay, lighting load 600 watts, it could be 10, 60 watts light bulbs maybe, direct current. The next load will be a coffee maker. Coffee maker it's a pure resistive load, so it falls under direct current circuit. The total wattage of the coffee maker is 750 watts. Okay, and the next load will be a heater. Heater is still considered to be a resistive load, and the total wattage of heater, we use this one during winter time. If it's cold outside, we try to open our heater, and the total wattage is 1200 watts. To make it a simple problem, the problem is just asking what will be capital letter R with the subscript T, meaning the total resistance. If we try to combine the total resistance of the three loads, the problem is asking what will be the total resistance. So this is capital letter R with the subscript T. If we try to combine the three loads, the next requirement of the problem is what will be capital letter I with the subscript T, meaning the total current circulating. It should be a common current because there is a current passing through the lights, there is a current passing through the coffee maker, there is a current passing through the heater. And since the connection is a series, okay, this should be the same as I total, and so with this, and so with this one. Because the determining factor for it to be a series connection is that the current passing through all the components should be common, so we could say that the connection is a series connection. Okay, so what is being asked for number 2 is the total capital letter with the subscript T, meaning the total current. Next one, this is capital letter R with the subscript L, meaning the resistance of the lighting load. This lighting load, which comprises of 600 watts, there is a resistance, single resistance of it, and we designate that as capital letter R with the subscript L. Next one, the heater, the total wattage is 750 watts, but there is a corresponding resistance for that one, and the problem is asking what will be capital letter R with the subscript C. meaning the total resistance of the copy maker. The last one, for the heater, there's a corresponding resistance. Okay, we are given the total wattage, and the problem is also asking what will be capital letter R with the subscript H, meaning the resistance equivalent of this 1200 watts. As simple as that one. Okay, let's proceed with the solution. We are to solve this problem here by using the concepts of series connection. So for a series connection, okay, I place it here. Capital letter, no. We'll do with the power first. Capital letter P with the subscript T is equal to, this is a sigma notation, and this is referred to as summation. Okay, summation of P. For a series connection or parallel connection, but for the meantime we are considering a series connection, the total power of the entire system will be the summation of the individual powers. Okay, and the individual powers are actually three. It's the lighting load, the copy maker, and the heater. So if we try to compute for the total load of this figure here, or this system here, the total power designated by capital letter P with the subscript T will be the sigma notation, or it's just simply the summation of the individual powers. Okay? Before we could proceed for the computation of R total, we will pass first for the computation of P total. We need that one. So taking the summation, this is 600, this is plus 750, this is plus 1200. The operation here is just a simple addition. Okay? They are all real numbers. Okay? Because for the meantime, we are on this circuit. If we are adding something, just add it as simply as that one, because we are adding all real numbers. That's the difference of DC from AC. That's why DC is much more simpler in the so-called addition. So 600 plus 750 plus 1200, they are all real numbers. So if we try to take the sum, this will be 2550 watts. As simple as that one. There is no imaginary part. We are on this circuit, right? So this is just a pure real part. Okay? To compute for R total, we will be using a relation here. And since we are studying engineering, okay, we must have to use an equation. And one of the equations under DC circuit is power is the square of the voltage over resistance. That's a general equation. So if we are talking for the whole system, if we now try to compute for this R here will be the square of B all over P. It is the square of B all over B. But I will now try to place the proper subscript. We are talking of the total system already. So I will place the subscript T, right? So capital letter R with the subscript T, meaning the total resistance of the entire system, should be equal to the total voltage applied to the system. The total applied voltage is 120 all over capital letter P with the subscript T, meaning the total consumption of the entire system. That's why I told you a while ago, we must have to compute first for this one before we could compute for R total, because we are given the total applied voltage. Okay, so by using this relation here, we are all engineers now, right? The total applied voltage to the three loads is 120, right? So they should be 120 square. And the total consumption of the three loads, which are connected in series, is 2550. So if we try to compute this one, that's a simple matter now. 120 square is 14,400 over 2550. And the total resistance is 5.647 ohms. Meaning, the single equivalent of these three here if we try to compress it as one single load, the total single equivalent resistance will be 5.647 ohms. This is very important because by knowing this, we could now compute for the total current, okay, drawn by these three loads here. So again, by using another relation, we are now all engineers, we are using equations on how to compute our unknowns. So by using another equation under DC circuit, that is power equal to the square of the current times resistance. Okay, we are given the power now, total true power. We are now given the total resistance of the entire system. So if we try to compute for I now, algebraic manipulations, okay? We divide both sides by R. What remains on the right will just be simply I square equal to the ratio P over R, right? But to compute for I without this power to here, we must have to raise this to the 1/2. So I square raised to 1/2, this two here cancel with this, so it will now just be simply I total. And the ratio P over R raised to the 1/2 is just the square root of P total over R total. Okay? Square root is just the same as P over R raised to the 1/2. I just changed the view, right? Since we are now given P total as per our computation is 2550. R total as per our computation is 5.647. And if we try to take the ratio of this, it's the square root of 452.12. The square root of 400 plus is 20 plus. So the total current is 21.25 amperes. So this is 21.25 amperes. The circulating current with the three given loads, which are connected in series, as per our computation, it is 21.25 amperes. Okay, so we are now given the total current. We have computed our total already. We computed I total, and the problem is asking what are the individual resistance equivalent of each load. So again, by using another relation, or same relation, power is equal to I square R. Again, if we try to compute for R, we'll divide both sides by I square, right? Divided by I square. So the right hand side, I square over I square cancels. So what remains on the right will be R. And for the left hand side, it will be the ratio P over I square. Right? So this will be the formula or equation on how to compute for the individual resistances of each load. So I will now try to place the proper subscript. If we now try to consider the lighting load, okay, the resistance of the lighting load now, it is just designated capital letter R with the subscript L. This L here refers to lighting load, equal to the power of the load over I total square. I total square is actually I sub L. But since the connection is series, the current passing through the lights is the same as the total current, right? So I just place I total quantity square. The total power of the lighting loads is 600, right? Total current is 21.25 ampere, quantity square. We square this one, this is almost 400. So 600 over 400, that's 1 point something. So the resistance of the lighting load, okay, is 1.328 ohms. Okay. For the copy maker, we will be using the same formula, but we will be replacing the subscript. We are now computing for the single equivalent resistance of the copy maker. So this is capital letter R with the subscript CM, meaning copy maker, equal to the total wattage of the copy maker is 750. Am I still on camera? over 21.25 square. This is 400, 750 over 400, that's less than 2, right? So the resistance, okay, of the coffee maker is 1.661 ohms. Okay. Let's try to consider the heater. Again, by using the same formula. So it should be the total, the resistance of the heater will be capital letter R with the subscript H, and this H here refers to the heater, equal to the total wattage of the heater is 1200 over the square of the current. And the value, this is 400, right? 1200 over 400, it's almost 3 ohms. But this is more than 400, right? So the total value of R with the subscript H, meaning the total resistance of the heater, is 2.657 ohms. The resistance is greater because the wattage is 1200 and this is just 750 and this is 600. So this is the smallest resistance, next in line, and this is the biggest resistance. And to check the validity of the value of the individual resistances, okay, we will now be using the concept of series connection. Like what I said, the total resistance of a series connection is just the summation of the individual resistances, right? So R total for a series connection, this is sigma notation, meaning summation of the individual resistances. So this is 1.328 plus 1.660, the next one, 61, and the last one is the resistance of the heater, that is 2.657. And if we try to take the summation of this by using our calculator, the single equivalent after taking the summation is 5.647 ohms, and it tallies with the computation R total 5.647 ohms. So our individual value, computed individual value of the resistances are all correct. 1.328, 1.661, and this is 2.657. Okay, that's it, guys. This should be a good illustrative example on the computation of a DC series connection. So for those of you who would like to subscribe or watch my channel is at youtube.com/@ProfDBJDeLosReyes. If you want to share it, please click share. Okay, good afternoon from Los Angeles.